Alrighty, we have a rather lengthy warm-up. So for this function, find the zeros of a function, then perform a sig analysis of the function. Determine the derivative of this function, and then find its roots. Then perform a sign analysis of the derivative. Over what intervals is the function increasing, decreasing? At what domain values is the function neither increasing or decreasing? Locate the domain values for any local minima, maxima, or plateaus. And what is it at each spot? And then sketch the function. So let's do this now. So go ahead and pause the video and try to do as much as you can. Alright, for the first one, to do a sign analysis, we first have to find out when it's positive or negative. When are we above and below the x-axis? So there are two things I do notice, that we have a 3 to worry about, due to this one, and a -2. So, at -2, to the left, when you plug in, like, let's say a -3, so let's try that out, -3 and -3, what will we get? Well, the first term, this term would be positive because of the square, and this term would be negative, so it will be overall a negative value, negative. And then let's plug in 0, so it's going to look really bad. So 0 here and 0 there. We would have a, and then again, we would have a positive because of the square. And over here we would have a negative again. So positive times negative will indeed give you a negative. And then for the last one, if you plug in a huge number like infinity, I'm not even going to put it in there. But infinity would be positive and then positive, which would give you positive. So let's put a positive there. So here's our sign analysis. What's the next thing it's asking? Find the zeros, which is -2 and 3 for a function, then perform a sign analysis. Yeah, we did that. Determine the derivative of the function f prime, and then find its roots. Then perform a sign analysis of the prime. So we have this. We do the product rule plus the chain rule, which we did in here. Let me go ahead and highlight so we can talk about it. So given that we have a square here, that's why we put this right here. So the derivative of the first times the second plus, and then that's a 3, the derivative of the second times the first. Another thing is we notice that we have an x, that we can factor out some stuff. We can factor out one of each, so we can factor out an x plus 2 and an x minus 3. Actually, 2x minus 3s, because over here we have 3, and over here we have 2, so we can factor out 2 of them. And we should end up with the inside the way we have it. The reason why we want to factor it is that's actually what you have to do in order to do a sign analysis. And then, when all is good and done, the inside here should end up giving you 5x, which is what we got right here. And then the x plus 2 and the x minus 3 squared. So the zeros would be -2, 0, and +3. +3 from right here, -2 from right here, and 0 from right here. At this point, we want to do a sign analysis, just like the way I did before. And when you do that, when you plug in random numbers, so let's say negative infinity would give you a negative here, and a positive here because it's squared. So negative times positive would give you a positive, hence the positive sign. And then when you plug in a number in between, so let's say -1, we would get a negative, we would get a positive, and we would get a positive. So negative times positive is negative, hence the negative. And then, excuse me, let's plug in a 1, so that would be positive. Plugging in 1 here will give you positive, and then a positive, so that's why we have a positive. And lastly, let's plug in infinity. So that would be positive here, that would be positive here, and that would be positive here. Also, a positive. So we have a sign analysis. We know when the derivative is supposed to be positive or negative. Or what intervals is the function increasing and decreasing? Well, for asking when the function is increasing and decreasing, we technically didn't need this analysis that I did right here. We only needed this one. Did I even ask for an analysis for that one? Find the zeros of a function and then perform a sign analysis. Okay, it did. I know why. Oops, let's undo that. So looking at that, we definitely have from, let me use green to talk about it. We definitely have a positive at negative infinity to negative 2, but of course you do not include infinity or negative 2 because derivatives at 0 do not, when the derivative equals 0, it doesn't tell you whether it's increasing or decreasing. We have a negative between negative 2 and 0, so that's why we put a decreasing right there. And then we have a increasing from 0 to infinity, not including 3, which is why we still have to separate them. Very often you might be tempted to actually write down 0 to infinity, but that includes 3, and given that 3, the derivative is 0, that will be an illegal move. Alright, part B. At what domain values is the function neither increasing nor decreasing? Well, that will be when the derivative equals 0, which are these values right here. And then locate the domain values for any local minimum, maximum, and plateaus. Well, when we look at this right here, and I think at this point I have to pick a different color. Let's go ahead and put gray. When your derivative was positive. Oops, that's not what I want to do. Go highlight it. Okay. When your derivative is positive and then moves to a negative, that kind of tells you that something was increasing and then decreasing. That would be a local maximum. When the derivative was negative and then becomes positive, that means it was decreasing and then increasing. That would imply a minimum. And then when you go from positive to positive, it means that you didn't really change. So that implies a plateau, meaning you were increasing and then you were still increasing. So the maximum would happen at negative 2, the minimum would happen at 0, and then the plateau would happen at 3 for those reasons. I hope that was clear. So I kind of showed it. This right here is when I talked about the maximum, this is when I talked about the minimum, and this is when I talked about the plateau. And then sketch the graph of f of x. So in this case, you can pretty much have a good idea after having done this one. We're supposed to be in negative from, I'm talking about this guy right here. We're supposed to be in negative before 2 and remain in negative, so bounce at negative 2. Boom, that's kind of what we did. We were in negative, we bounced. And then after 3, we kind of go to the positive because as you can see, that was a positive. So at 3, we kind of continue to go through. You probably also want to find out what that value is, that y-intercept. In this case, it wasn't mentioned at all. And that's it. Let's move on. This is going to be a good time for me to introduce the group project that we're going to do the next day. So what I want you to do is, whoa, what did I do? What I would like you to do is, I would like you to be in groups of 4, if needed, or 3. And you're going to be using trig identities and the quotient rule to work on with your group to find the derivatives of the trig function I'm about to give you. Then write your work on a poster, or in our case, a board. I'm going to have 2 whiteboards for you guys to work on, and that's happening tomorrow. But for right now, you need to take notes. So here's some fundamental trigonometric properties that you should already have, which is sine squared plus cosine squared equals 1, 1 plus tangent squared equals secant squared, and 1 plus cotangent squared equals cosecant squared. And you should already know what this is. Like, what is this? What goes in here? What is it? What's this mystery one? What's this one? Oh, and then what's this one? They're all copliant. All right, anyways. And so these are some identities that I probably am not going to tell you right now. I'm going to tell you when you guys come the next day. This is what you're going to be working on. So I'm still going to figure out which one you're going to do when you come in tomorrow. And let's move on to our notes. So we want to talk about tricks of derivatives. By the way, if I expose an answer right now that comes from the group work, it doesn't really matter because you're supposed to be using trig identities and the quotient rule to prove it. So if you guys see the answer here, good for you. So this is the ones that we've already covered, but now here's some new ones. Derivative of tangent is secant squared. Of secant is secant tangent. Of cotangent is negative cosecant squared. And cosecant is negative cosecant cotangent. You're probably picking up a pattern right here. Like this seems very similar to this, but like the other one. So for tangent will be secant squared, but for cotangent will be cosecant squared, but with a negative. For secant, it will be secant tangent, but for cosecant, it will be negative cosecant cotangent. Let's continue. Alrighty, so go ahead and do these derivatives, pause the video, and give it a good try. Alrighty, assuming that, I'm not exactly sure what was expected for this one, but assuming that u is not a function but just a variable, then you would pretty much have cosine. Oh, is that too large? Yeah, that is way too large. Alrighty, it would be cosine of u. But if u was a function, then it would be cosine of u, that doesn't look like cosine, times u prime because of chain rule. So that was an easy one. And then same thing here, I'm not going to waste your time on it. For secant, what was it again for secant? It was secant u tangent, tangent u. And if it was, if this was a function, u was a function, it'd be u, come on. You're better than this, Mr. S. U prime secant u tangent u. Okay, that looks horrible. Actually, that C right there looks pretty cool. Alright, and then you get the gist of it. So go ahead and finish this in your notes and then show them to me the next day.
You're better than this, Mr. S.
Yes, I am. Alrighty, secant 4x to do the derivative. It's pretty much a chain rule, so you follow it the way you usually do. So it would be tangent 4x, secant 4x times 4, or just this way. Let's move on. To do this one, that's a chain rule within a chain rule. How fun. So, x to the 5th would be, you gotta move to 5 to the front. So that would be 15, and then leave the inside the same. Tangent to the 4th power of 7x. Then the derivative of tangent to 7x will be secant squared 7x, and then the derivative of 7x will just be 7. And then when all good is done, you should have this one right here. Alrighty, and then we have some problems right here for you to work on, and I am really conflicted. I feel like I should be doing these problems on the video for you guys to watch, but at the same time you should try them. But I can probably just isolate like certain one of them and just do some of them. Like for instance this guy. What do you do for number 14? It's a chain rule, right? So 88 times 11 over 8, and then cosecant of, and then 1 minus that, so that would be 3/8, times the derivative of the inside, which is cosecant, if you remember, was negative cosecant cotangent. And I'm completely going by memory, so I could be completely wrong. That's 2x, by the way. 2x. And then times, and then 2x. And you probably would want to make that look prettier. And that's that one. I was just about to put multiply by 2, but I just realized that in the previous one I showed that 2x, and that is not 2x because the derivative of 2x is 2, just to clarify that. So just multiply that by 2 again, whatever that times 2 is. Making these pretty is not that easy. So just change that one up to 242, negative. And then keep the other stuff the same. Really difficult to make this one look any nicer. And these cannot be combined anyway, given that, well, they do have the same power. So I guess I can combine this guy and this guy. But I don't want to say stuff I'm not sure about. Yep, they have the same insides. And I don't think if I made a mistake, just correct me when I see you guys the next day. But it seems to me like you probably can say cosecant and then +1, which is 11. eighth, and then 2x, and cotangent of 2x. Yeah, just multiply. Alrighty, so I'm gonna leave it at that. These are a little bit easier. I think this one was the most complicated one, the one I just did. This also kind of looks pretty cool. Look at that. Look at that. Alrighty. So, go ahead and pause the video now, work on these, and show me what you get when I see you guys tomorrow. Have a fantastic day.